Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on graph theory, lecture number 37, in which I will derive Euler's formula for planar graphs. We know that a connected planar graph G may have several planar representations. Here we see graph G in figure 1. This is a graph G. Here we see that this graph is drawn on a plane, but edges E3 and E6 intersect with each other, so this is not a planar graph. We may draw the embeddings of this graph. That means we may have planar representation of this graph in figure 2 and figure 3. Therefore, for a given graph, we get here two types of planar representations. Here we see that graph has vertices V1, V2, V3, V4 and edges E1, E2, E3, E4, E5, E6. Here we have regions R1, R2, R3, R4. 4 number of regions in the figure 2. Means in one type of planar representation we get 4 number of regions in figure 2. In second kind of planar representation of the graph G in figure 3, we have vertices V1, V2, V3, V4 and edges E1, E2, E3, E4, E5, E6. Also regions are R1, R2, R3, R4. 4 number of regions. So if we take different planar representations but number of regions remains same, by Euler's formula we will prove this. So firstly we state a theorem. Theorem is, let G be a connected planar graph with V vertices, E edges, has E minus V plus 2 number of regions. Or we may state the theorem in another way. Let G be a connected planar graph with V number of vertices, E number of edges and R number of regions. Then V minus E plus R equal to 2. This formula is known as Euler's formula for a planar graph or map. Now we prove this. Let G be a connected planar graph. We shall prove the theorem by method of induction on number of edges of graph G. Firstly, we take number of edge equal to 1. Let number of edges, that is E, equal to 1. In this case, we get two subcases. Number 1, number of edges E equal to 1 and V equal to 1, number of vertices 1. Number 2, number of edges 1 and number of vertices V equal to 2. For 1, we get a loop. Here vertex be V1 and edge be E1, one number of edge and one number of vertex. Here we have two regions, R1 and R2. Where R1 is finite region and R2 is infinite region. Therefore, number of regions are equal to 2. Hence, V minus E plus R equal to V is 1, E number of edges 1 and number of regions 2. That is 1 cancel 2, implies that V minus E plus R equal to 2. Therefore, formula is true. In this subcase. Let this is number 1. For subcase 2, here E equal to 1, number of edges 1 and V equal to 2. Therefore, graph is this is V1, this is V2. If this is figure 1, this is figure 2. Here we see that we have only one region. Here region R1, which is infinite. Therefore, number of regions are equal to 1. Therefore, V minus E plus R, V is 2, E is 1 and R is 1. This is equal to 2. Implies that V minus E plus R equal to 2. Therefore, the formula is true in this subcase. This is number 2. Let the formula is true for up to E minus 1 number of edges. This is number 3. Now we prove the formula for E number of edges. Here we may have two subcases. Number 1, the connected planar graph is a tree. Number 2, the connected planar graph is not a tree. For 1, since the graph G is a tree having E number of edges, we know that if a tree has n vertices, then it has n minus 1 number of edges. Therefore, if the tree has E edges, then it will have E plus 1 number of vertices. We know that every tree has only one region, R1, which is infinite. Here we see this is a tree. We see that here only one region R1, that is infinite. Here we do not get any circuit. If we would get circuit, then we get different regions. So we do not get any bounded region. Tree is unbounded. So unbounded region is R1, that is infinite region. Therefore, number of regions are equal to 1. Therefore, in this subcase, number of vertices equal to E plus 1, number of edges equal to E, number of regions are equal to 1. Therefore, V minus E plus R equal to V is E plus 1, E is E, and R is 1. Here E and E cancels. Therefore, remains 2, implies that V minus E plus R equal to 2. This is number 4. Therefore, in this subcase, formula is true. Now, for subcase 2, here number of edges equal to E. The connected planar graph is not a tree, implies that there exists at least one circuit in the graph G. Let E1 be an edge in the particular circuit of graph G. If we remove the edge E1 from G, we will get that two regions of graph G minus E1 will merge and form a new region. Here we see that E1 edge is in the circuit E1, E2, E3. Here if we remove E1, we get that the region R1 and R2 will merge and will form a new region. This will be the one region. This one region will be formed by edges E2, E3, E6, E5 and E4. That is, number of regions will be reduced. Therefore, in this case, number of vertices V, number of edges. Here we have removed one edge E1, so number of edges will be E minus 1. Number of regions will be R minus 1. Since G minus E1 graph has E minus 1 number of edges, therefore the formula must be applied here. Hence, number of vertices minus number of edges plus number of regions equal to 2 implies that number of vertices be V, number of edges be E minus 1 and number of regions is R minus 1 equal to 2 implies that V minus E plus 1 plus R minus 1 equal to 2 implies that here 1 and 1 cancel. So V minus E plus R equal to 2. Therefore, the formula is true in this subcase. Let this is number 5. Therefore, from 4 and 5 we get formula is true for number of edges E. Hence, formula is true for any number of edges. Hence, proved. Now we prove the next theorem. Next theorem is, let G be a connected planar graph with V vertices, E edges, and V is greater than equal to 3, then E less than equal to 3V minus 6. Now we prove this. Let G be a connected planar graph such that V equal to number of vertices, E equal to number of edges and R equal to number of regions. Also given that V is greater than equal to 3. Since we know that degree of a region is the length of the cycle or closed arc which borders the region. Since each region is bounded by 3 or more than 3 edges, here we see that this is a region bounded by 3 edges, or we get more than 3, here 4 edges. These are regions R1, this is R2. So, therefore, total sum of degree of all regions greater than equal to 3R, R be the number of regions. One region has at least 3 degree. Also we have more than 3 degree. So this inequality holds, sum of degrees of all regions is greater than equal to 3r. Let this is number 1. We know that total sum of degrees of all regions equal to 2 multiplied by number of edges. This is number 2. From 1 and 2, we get 2e greater than equal to 3r, implies that 2 by 3e is greater than equal to r. This is number 3. By Euler's formula, for connected planar graph, V minus E plus R equal to 2 implies that V minus E, here R is less than equal to 2 by 3. If in place of R we write 2 by 3E, then it will be greater. Greater than equal to 2 implies that 3V minus 3E plus 2E by 3 greater than equal to 2 implies that 3V minus E greater than equal to 6. 3 multiplied by 2, 6, implies that 3V minus 6 greater than equal to E. We may write this E less than equal to 3V minus 6. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.